All right. So the relationship. This is going to be your first right-hand rule, and there are multiple right-hand rules that you're going to learn in this unit. The one that you've probably all seen physics students using is this one. We call this the physics gangsta symbol. It's a little different from. Doesn't Mr. Shilio have like a gangster symbol as well? Yeah. But we're going to be using two right-hand rules when studying electromagnetism. The first says that when current in a wire moves in a particular direction, a magnetic field will be created in a circle around the wire. Okay? So that magnetic field, we use the symbol B to relate magnetic field strength. And the direction is going to be important. And one of the reasons I wanted you on last night's homework to draw little compass arrows is that's how we're going to think about the magnetic field. So magnetic field and electric field lines now will need to be three-dimensional. So vectors can be up, down, left, right, in the plane of the page or the board, or out. Okay? Think of this as an arrow. This is the head of the arrow, the tip of the arrow coming out of the board pointing at you, like an arrow, like bow and arrow, not a vector arrow, an actual arrow. This is the feathery part, the fletching on an arrow. So that's like the tail of the arrow. You're looking at the tail, so this is going into the board. Got it? All right. So in a current-carrying wire, if you use your right hand and you lay it down so that your thumb points in the direction of the current, your fingers will wrap around the wire. Actually worked pretty well. Your fingers will wrap around the wire, and the magnetic field will point in the direction of your fingers. So if I go up to the board and I do this, you see how if my thumb is the wire and I grab the wire, then the magnetic field will point out of the board on the right side of the wire, into the board on the left side. If you use your right hand, it will always work. Okay? Somebody, because it happens every year, will use their left hand when taking the test, and will get half the questions wrong. Yeah. Any orientation, absolutely. And by the way, it's not usually lefties that make that mistake.
Because you're writing with your right hand.
Right. You're writing with your right hand if you're a righty, and then your left hand is available, and then everything's backwards. Okay? Let me show you using a piece of equipment that, as you know, I name things like my calculator and Betty the microwave. Well, this is Bertha. Yeah, this is Big Bertha. It doesn't matter how you look at it, honey, it always works. So Bertha is a very heavy power source, and she's got to be older than I am. Lots and lots of current and voltage is produced by Bertha. It would be difficult to purchase Bertha legally for school use, put it that way. So I'm very, very cautious about students using Bertha. It's a bad idea. Today I forgot to turn her off, and a wire disconnected, and so I went to just connect it. Yeah, bad idea. I've been shocked by Bertha before, and it hurts a lot. So you will not be playing with Bertha.
Aww.
Yeah, sorry, Stephen.
Could it be fatal?
Yeah, under the right conditions. She pushes easily probably 15 to 20 amps and higher voltage. So, all right. So what I'm going to do is reproduce the experiment that Volta was doing.
Ooh, frogs.
No frogs. Sorry, man. So I'm going to push a good amount of current through the wire. And we'll put a couple of compasses nearby, okay?
Can you make them
Now, these
more
compasses should, if we give them a couple
light?
seconds.
Can you move them into the light a little bit more?
Yep.
Thank you.
You're welcome. So those compasses should orient themselves. Hello, cooperate you. They're not the most expensive compasses in the world. They're not pointing north-south. Must be a sweet spot, that's fine. So I'm just gonna hold this wire near the compasses. Push some current through the wire. Probably should get out of the way so you can see it. And yes, indeed, they do move. Okay? And orient themselves in a way that's tangent to the magnetic field that's being created around this wire.
What would happen if you charged the little needle in the, holding the compass in place?
If you charge, oh, the needle itself, I'm sure it would have an effect. If somehow you could run current through that center spot.
Yeah. Would it spin around?
It might. If it's not perfectly centered, it would probably create some torque and then spin.
Cool.
So there she is again. And think about it, Volta told the student, stop bothering me, and then he stole the idea. So, all right. Well, let's take this effect now and magnify it. What were you going to say, Miss?
How do people know that's true?
How what?
How do people know that's true?
It's a story, so I don't know. I don't know that there's any, since the student can't speak for himself. So let's take the wire and wrap it into a circle, okay? And there's the current moving counterclockwise through the wire. A magnetic field will be created just like it was in this straight wire, and those magnetic fields will wrap around the circle, okay? So it'll look kind of like this. Now you're looking at these magnetic field lines, the pink lines, on edge. Does that make sense?
Yeah.
You're looking at them from the edge, okay? And if you use the right-hand rule, the question is, which direction will the magnetic field point at different spots? So let's do this one. This one's a little bit easier. I want you to tell me the direction of the magnetic field on the left side of the wire. So in the plane of the board or in the plane of the page, which way is the magnetic field pointing right here?
Or the,
Yes. So how would I draw that? Circle with a dot, correct. Does that make sense? So that's why it's important to have this vector representation. How about, tell me the direction right directly in front of the wire at that spot. Which way will the magnetic field point?
right.
To the right is correct. So tangent to the circle. Is that understandable? And on the rightmost side, the farthest side away from the wire on the right, which way will the magnetic field point? Yeah, that's going to be the fletching part of the arrow, right? Okay. So let's do the same thing here. I want you to take your thumb, lay it down, and figure out the direction of the magnetic field. So whenever you have loops, the rule is your thumb points in the direction of the current, and your fingers need to plunge through the center of the loop. Not outside the loop, but inside the loop. And it will be helpful if you bring your own loop to class. So if you have like a rigid bracelet, that's a really nice thing to bring because we're going to be using loops a lot. I do have some that I've made, although in the move I'm not exactly sure where they are, but I'll keep looking for them. And they're made out of pipe cleaners, so they're not quite as nice and rigid. So here's the loop. The current is counterclockwise, correct? And so it doesn't matter where I grab the loop, notice which way are my fingers pointing. On the inside, which way? Out at you, right? If I grab the top, they're still pointing out at you. If I have my thumb go counterclockwise over here, they're still pointing out at you, right? So the magnetic field will be wrapped around like this. Does that make sense? So I want you right now in your notes to draw, like we did over here, to draw the direction of the magnetic field inside the loop. So that would be the farthest most point inside the loop toward the center. Just if you're scared that you're going to do it wrong, just draw it lightly and then feel free to use your right hand. This is my favorite test because kids always end up like doing contortions while they're taking the test using the right hand rule. And that's just fun to watch. I don't care. It never gets old. Never gets old. Been doing it for 28 years. I'm like, look at you laying on your desk. So your thumb is the wire. Lay your thumb down on the page and pretend to grab that wire and tell me which way do your fingers point on the inside.
Arrowhead.
Arrowhead. That is correct. Good. Thank you, Wes. Conversely, which way will the magnetic field on the outermost
Like goes
edge
line,
point?
Like up the line.
Right here, here, here. What part of the arrow?
Oh.
Yeah. So these dots represent out of the plane of the page or out of the board, and the X's represent into the board. Now looking at the field density, where are the lines the most dense? Inside. These are the most concentrated. So that's why when you were in middle school and you made the fishing pole, the electromagnetic fishing pole, you always wrap the wires around the fishing pole, okay? Around the core that you're going to be magnetized, because that's where the strongest overlap of the magnetic field is. All right.